Great. So I'll tell you, this is a quick overview of how computing is used in my group and how we embrace basically problems that are very significant in society, in science in general, through this combination of physics and computing. So we call this physics-based modeling and computing. So in general, what characterizes my group is we have these pillars in which we have a problem where we are trying to answer a question. Let's say, I'll use this car as an example. We want to design this car, basically make it more aerodynamic to minimize energy, let's say. But we cannot test 1,000 of them, right? So we are going to invoke computation to help us in designing it. So the pinnacle here, or the foundation, is that we start with physics laws, like conservation of energy, conservation of mass, and so on. And then based on those, we built a mathematical model of basically on those laws that will allow us to answer the questions at hand. Most of the time in my group, these models come in the form of differential equations, partial differential equations. And what happens is the quantities that we are interested in, for instance, the velocity at a point in the car, you cannot find them in an analytical way. You cannot write a formula that will give you this in the system. So what happens is then we need to invoke numerical techniques that immediately connect to computing to approximate the solution of those, or of these mathematical models, or approximate these quantities of interest. So that is in general the foundation, or those are the elements that permeate in basically in a lot of the things that we do. And I'll give you some examples now, some concrete examples. The next slide. So for instance, one of the huge impacts that computing has had is minimize physical testing. There are tests like the one that you're seeing here, let's say an airplane, we are interested in understanding, the robustness of a design of an airplane, and we're going to crash it and understand how it works. Well, we cannot do a lot of those tests. So we have evolved to the point that we can do simulation and answer fundamental questions that we may have about this. We may not be accurate in every single aspect of the problem. For instance, we cannot predict the deformation to a millimeter of the airplane, but we can probably come very close to say what is the maximum energy dissipated in general in the airplane. And we will agree that we cannot do many of these tests. This is the same in crashworthiness of cars, for instance. This is used a lot. There is more simulation than testing actually done in car manufacturing. Next slide. All right, so, and I decided to just show you one example of an actual project that we have where we use computing is essential to provide some of the answers that we're looking for, and it is related to the medical field. This project is in collaboration with Matt Urban and Jim Greenleaf from the Mayo Clinic and Murthy Gudati from NC State. This is an ongoing project, and it's basically computationally assisted arterial disease diagnosis. Next slide. So the problem consists in basically we want to diagnose arterial disease, and for this we start recognizing why is that important, or what is important in that problem. So stiffness is at the heart of the problem here, because it's recognized as an independent risk factor for adverse vascular events. An event just simply could be heart attack, stroke, and so on. So arterial stiffness results primarily from changes in the collagen structure of the artery and the median layer, so elastins and fragmentation, deposition of collagen, and so on. And the goal is to be able to non-invasively estimate the stiffness of the artery and use this as a biomarker for disease. Next slide. So to do this, we have three components that we need to address. One is to acquire data non-invasively. Then two is extract information from the data. And number three is make the diagnosis based on the data. So the first component that we're using this is the collaboration with Mayo Clinic, is using ultrasound, but a very particular aspect of ultrasound, the radiation force of ultrasound and tracking of waves generated with ultrasound. So this is very different from the conventional ultrasound that you see today in clinical applications that is common, where you just use it to basically generate an image from a scattering of the particles when you send the ultrasound waves. In here, you use ultrasound to generate a force, launch a wave, and then monitor the wave. So by doing this, we can do remote palpation in essence. So we do this in arteries, specifically in the carotid artery around your neck, to launch waves, monitor the waves, and those waves carry information about the collagen and elastin structure that is in the arteries, and those are connected to disease. So that's the link that we're following. However, when we monitor those waves, it's not easy to tell what is the collagen content that is in there. And that's the problem I'm going to try to address through computing. Next slide. So in here is an image of one of those computational models of the artery. It just looks pretty benign. It's just like a cylinder, but we launch waves here that are really complicated, and we monitor those waves with ultrasound probes. Now we have at our disposal a model like this. How do we use it? Next slide. So this is the heart and soul of how we will use that model. So the first component here is the mathematical representation of how the waves propagate in the medium. We call this an elastodynamics boundary value problem. So here, this is a representation literally of Newton's second law, force equals mass times acceleration. And we have a representation of the connection between the material in terms of stresses and strains, boundary conditions, and so on, right? So this is the problem that we solve using the computer and the model that you saw in the previous slide, because we can predict how the waves propagate. With that at hand, if we can solve the problem in the top, then we can ask the question, okay, given the measured data with ultrasound and the fact that I have that model, can we recover the mechanical properties of the artery over the heart cycle? That's an inverse problem. And we solve that through what we call a partial differential equation constraint minimization problem that is depicted in front of you on the bottom of the slide here. And the solution of that optimization problem are the mechanical properties that we are going to use now to be able and use those or connect those to biomarkers and trying to separate patients into different levels or different groups with different risks. Next slide. And this is the last slide I wanted to show you. This is a reflection of actually everything that I was telling you and why and the end result. In here, what you're seeing on the left is the phase velocity of the principal mode of propagation of one of those waves that I'm talking about that we launch with ultrasound. And the one on the right is the right carotid artery. The black markers represent healthy patients. The blue ones are atherosclerotic cardiovascular disease confirmed patients, and the red ones are patients with cardiovascular disease risk factors like having diabetes, being obese, smokers, and so on and so forth. So as you can see here, the healthy patients have wave speeds much lower than the patients with confirmed disease and patients with risk factors. And this is consistent with the fact that there is less collagen and less elastin fragmentation in those patients, basically. And this is the premise of everything that we're doing, going directly from the measurements to information like this to be able to diagnose arterial disease. And I'll stop here in the interest of time and take questions later. That's it, Jonathan, back to you.